Hi, I'm Spencer Garrett, and this is my Capstone video for my Coursera IBM Advanced Data Science specialization. And I hope you guys find it informative and enjoyable. For my project, I chose to attempt to forecast the number of positive coronavirus cases for the United States, at least for the next day. For my data set, I was able to get it from the COVID tracking project. They had a U.S. data specific set that they update daily between 4 and 5 p.m. And the initial data set I got is from January 22nd, 2020 to August 23rd, 2020. And within the model that I used, which ended up being an ARIMA model, I also incorporated data from January 22nd to August 25th in order to test the model that I had trained. And the use case for this sort of model is in order to kind of clear up any uncertainty caused by COVID-19, which can lead to kind of restlessness by not being able to see where you're going and really limit your decision making capabilities. So it's an attempt to provide more clarity within that realm. And here is the code at work and what the prediction was in comparison to what the actual case count was for August 24th and August 25th, 2020. So right here, we can see the actual data for the 24th and 25th. So you can see that for the 25th, the prediction is 5,755,472. And if I go back in this video a little bit, sorry about that. Right here, you can see that the actual number of cases on the 25th is 5,749,083. So the difference is only about 5,600 cases, which isn't terrible. It overshoots it a little bit, as you can see illustrated in oops, illustrated in this graph right here, which shows the actual as the blue line and the predicted as the orange line. And in some senses, it might be better that it overshoots the prediction because you can kind of be more, you at least know what to expect and you're not going to be surprised by the case count for the next day. And also operating with this data set that is updated daily, you can also keep running this algorithm daily and predict 2 days out, even more days out, but the error is going to grow the further you predict into the future. So it also depends on the types of decisions you're looking at making, and this would be better in regard to any short-term decisions as you're looking at cases and kind of the situation that the U.S. is going to be facing as a whole for the next couple days. And now more details about the architectural decisions that I made during this project. Again, you can see the data source right there at the top bullet point. For data integration, I was using Apache Spark within a Jupyter notebook that was operating within Watson Studio. And for the initial discovery and exploration of the data, Pandas was the biggest help. I was able to manipulate drop rows, add rows, run any aggregations that were necessary in order to get a better feel for what this data set contained and what story it was telling. And Matplotlib and Seaborn enabled me to produce visualizations that were super beneficial in kind of painting a picture of what the data had to offer and what the trends were within it. And then in order to produce the actual actionable insights in the solution, I worked with Python because I'm familiar with that coding language. Pandas, again, is a great help. Scikit-learn for some of the machine learning models that I attempted, such as linear regression, logistic regression, and the Holtz model, or sorry, the stats models is what enabled me to use the Holtz model as well. And that also enabled me to run the ARIMA model, which is the one that ended up producing the best results. Linear regression, logistic regression, there was enough data for it, as was the case with the Keras model using the TensorFlow as the back end. That one also didn't produce great results. It was undershooting all of its predictions. And that's just due to such a small data set. And for data quality and pre-processing, I started out with data that was state specific, but that ended up not being functional because of the way that data is recorded between each state. However, looking at the US overall, I was able to get pretty good and full stats for positive cases recovered and deaths. However, deaths and recovered had null values, so I filled them, but didn't end up running any analysis or machine learning algorithms over them, so I didn't have to deal with them in that sense through the machine learning algorithms. I did have to reverse the order of the data set to have the most recent observation in the last row so I could append the predictions properly, because initially it had those ones in the zero index for some reason, and I had to convert the date field to date time and then re-index the data set so that the date was the index. And this is the model performance. As you can see, one day out for August 24th, it was only off by 2,552 cases. And then only one more day out from that, so 2 days out from the actual data, it was off by 5,669 cases. So you'd expect that difference only to grow the further you project out. And the R-squared value, not necessarily the best performance indicator for this, because the actual and predicted sets only differed from each other by 2 data points. But the mean absolute error is also affected by the actual and predicted sets only differing by 2 data points. But it's not too bad, and I think the number of cases that it's off by and the fact that the point of this project is only to predict one day into the future and only being off by 2,500 cases makes it a pretty good model, especially when compared to logistic regression, ridge regression, linear regression, and the Keras models that I attempted to run it with. And those ones all just either under or way overshooting what the cases were. So here is the algorithm in full. That was loading in, re-indexing for date time, and then putting out some visualizations. I had to make the data stationary by taking the difference not once but twice to kind of center it around 0. And then these next 2 charts coming up right here, they help indicate how many variables of what the AR terms and the MA terms should be, and that's right here specified in the order of the model. And I did some playing around with that and tweaking, and this combination made the most sense, and 5 AR terms and only 1 MA term with a difference of 2 was producing the best results and the best prediction for at least one day out. And this is just a test for one day out, so you get August 24th. And then this next one is 2 days out, August 24th and 25th. And now, in order to test this data, run it through, and load in an actual data set containing the real values of August 24th and 25th. And here I'm just running through the initial data cleansing and getting it into the same format that I got the prediction data, with the date as the index and just showing the positive cases. There's the tail showing, again, August 24th and 25th right there. Pulling those out and then predicting these 2 days once again, but in a data frame of their own so that I can append it to the initial data set that I used to make those predictions. And here again, that was the initial visualization, but here is the zoomed in visual. And those are my sources. Huge help throughout the project. Thank you all for watching my video about my Capstone project relating to forecasting coronavirus cases for the next day. It was a huge learning experience for me, and I've really enjoyed working through everything that goes into a data science project over the last month or so. So thank you.